Okay, my best chem students at Allen High School, this is it. You've made it through your equilibrium. This is your very last video, and I know you're just going to rock on this test. So let's see one more equilibrium. This time I want us to look at a KSP problem, solubility product issue. So we've got a seemingly insoluble. Remember, we told you it's insoluble. According to solubility rules, it's insoluble. But a small amount will go in. And it does give us that. Notice that it says that the concentration of Pb2+ is found to be this. Now, I like to use rice for this. So let's first start with part 1 here, which is to set up the equilibrium constant expression. So KSP is equal to Pb2+. You have to use brackets because we're now talking about molarities, and it's to the first power times I- squared. Great. Nice, quick 1-point answer there. Now the question asks us to solve for I-, and I'm going to go ahead and set up a whole rice grid for this for you. Some people would say it's not necessary, but I think it's going to help give us some direction here. And this is where I like to identify what my solubility is. So this is, we have some, it's at equilibrium. As long as we have some, we don't care how much. Now, this started with, we added excess PbI2 to the solution. There is no other source of lead ion. We're not adding lead nitrate or lead acetate or anything like that. There's no other source. And there's no other source of iodine. Now, I like to use my little S here. So for every one of these, I get 1 lead. That means that my lead ion represents the solubility here. And this would be plus 2S. So this is S and 2S. The reason, again, remember, it's 2S because of that 2 right there. Now, it says first off to calculate the molar concentration of I in solution. Well, the problem told us our lead 2+, and that's what S is. So this was given that this S is 1.3 times 10 to the minus 3. So iodine must be 2 times that. So this is the answer to this one. Let's look here. My molarity of iodide ion is 2 times my solubility, or 2 times my lead ion. So I get 2.6 times 10 to the minus 3rd molar solution at equilibrium. Now, the last part of A asks us to then calculate K. All we need to do is plug in those values that we have. We have our lead ion. It was that given 1.3 times 10 to the minus 3. My iodide is 2.6 times 10 to the minus 3 squared. Don't forget to square that. So I know that's tad messy right there. Let me see if I can clean that up for you. 1.3 times 10 to the minus 3rd. That's what was given. So if you do that algebra and you crank it out correctly, or I cranked it out correctly, we'll double check each other. I get 1.79 times 10 to the minus 9th. And we don't worry about units here. All right, so they stepped us through this calculation, but you're the one who is going to have to remember to set up that rice as your framework. Sometimes it's more helpful than other times, but every time you approach these problems, it gives you a good solid scaffolding to approach your problem with. All right, now we've got a saturated solution. So part B, we have a saturated solution. We add PbI2 into 2, and we've got 2 liters of solution, right? And we're at 25 degrees Celsius. Now there's really 2 ways you could do this. You could kind of go backwards to K. Remember, KSP is equal to the solubility times 2 times the solubility squared, if we plugged in from our prior part. And we were given the solubility. So the solubility was given as being equal to the lead ion. We figured that out because it was a 1-to-1 mole ratio. And that's equal to, if you just did this algebra for our KSP, we could plug in our KSP, 8.79 times 10 to the minus 9th is going to equal 4s cubed. And if you solve for s, lo and behold, you're going to find the same values. S is still, if you solve this, you're still going to get 1.3 times 10 to the minus 3rd molar for your solubility. And the I is double that. So our I concentration, iodide, is 2.6 times 10 to the minus 3. That's the long way to do that. The short way is to note something here. Since the temperature does not change, the concentrations do not change. Your concentration of ions do not change as long as it's saturated. And the reason is that our solubility, which in this case was moles per liter, is intensive at a given temperature. It's already been normalized for our volume. It's already on a per liter basis. And so you could have just made that statement and not done any calculations. All right, let's see what happens in this next one. We're dealing with the same equilibrium. Solid NaI is added, and we have a solution that's already saturated. The question is, would our lead ion increase, decrease, or remain the same? So again, we've got PbI2 solid. All right, and that's going to lead ion plus iodide ion. Now, the key to this is to realize that NaI, sodium iodide, which is a soluble salt, goes 100% to sodium ion plus iodide ion. What we're doing here is adding a common ion. So now we can talk about it in terms of LeChatelier. So we have stressed by making a new Q. We've stressed it away from the equilibrium value. And by what we've done then is we've increased our I. We've increased the amount of I that we have. Sorry, let me start that direction. We've increased the amount of I. Well, that means we have increased our numerator, which makes Q greater than K, our new state greater than our original state. When Q is greater than K, that means we have to shift to consume product, that which we have too much of, and form reactant. And that means that our molar concentration of lead ion would actually decrease in this situation. Okay? So you would see a decrease in this. We would actually see an increase in the amount of solid that forms. Whoops, let me do that. An increase in the amount of solid that forms. Right? So. All right, now it's shifting to another KSP. Often these are long. Remember, this is your first question, always is an equilibrium, at least until 2014. This time we're given KSP and we're given volume is added to volume. When you have volume added to volume, you better remember to voom voom. Volume to volume, we need to voom voom. So we want to know the molar concentrations of each of these. Well, I'm adding barium nitrate. So let's start first with our barium nitrate. We need to do an ion within, and I hope you can now see that our concentration of barium ion is going to be equal to our concentration of barium nitrate because it's a 1-to-1 mole ratio. Now, our concentration of chromate, so Na2Cr O4, is also going to be equal to our sodium chromate because those are both soluble salts and it's a 1-to-1 mole ratio. You could do 2 stoichiometries to get that, but in an ideal world you can start to recognize it since these are both 1-to-1 mole ratios. When we do a molarity of an ionic to an ion within, those are equivalent. So what we have to do first is do voom vooms for each of these. So I have my initial is 500 milliliters. My initial molarity of this is 8.2 times 10 to the minus 6th. And my new volume is a liter. We took a volume plus a volume. Volume plus volume, got a voom voom. Times my new molarity of barium ion. And if you do that dilution, it's basically cutting that in half, we'd get 4.1 times 10 to the minus 6th molar is equal to my concentration of barium ion. Okay? Now, we're going to do the same thing with the chromate. We had, let me do it up here so you can see this a little better. So we're going to go up here to work. We had 500 milliliters as it's starting, and it was 8.2 times 10 to the minus 6th. I hope you're seeing that we have a variation on a theme, and you probably could have simplified this with a statement. My new molarity of chromate ion. Okay, and it too is going to be 4.1 times 10 to the minus 6th molar. All right, so that's the number 1 here. And now number 2, we want to be able to show, this gives us the claim, which is kind of nice. It doesn't ask us for the claim. It says, prove why it doesn't form. Well, remember, those are starting amounts. So the amounts up here are initials. Initial values are used to calculate Q, that non-equilibrium state. It's calculated the same manner, but with different numbers. Now remember, if Q is less than KSP, we don't have enough product. Our numerator is too small. And in order to achieve equilibrium, we're going to have to form product. Okay? Now, if Q is greater than KSP, it means that your numerator is too big. You can think of it in terms of denominator, but I tend to think just in terms of numerator. It's a little simpler for me. That means I have too much product. That means I need to consume product. When you form product, you consume reactant. When I consume product, I would increase reactant. In this case, our reactant is a solid, so we would see a precipitate form. So Q bigger than K, precipitate. Q less than K, no precipitate. So those are our 2 possibilities. All we have to do now is prove which one it is. So Q, let me go back because I realized we never really wrote the reaction for this one. So let's go ahead and write that. Here's our insoluble salt, BaCrO4. It's going to go into its constituent ions. I'm given initial conditions, so that's my reaction. We really don't need to get to the C and the E part, because Q, therefore, is going to be barium ion initial. I'll put a little I there as a reminder, times my chromate initial, which we found they were each equal to 4.1 times 10 to the minus 6th. So that's 4.1 times 10 to the minus 6 squared, which is equal to 1.68 times 10 to the minus 11. Well, we are given K up here. So that means that our scenario is that Q is less than K. So this is our argument here. We're not going to have a precipitate because the system can hold. Basically, you're not saturated is what this is telling us, is we're not saturated. The solution can hold more barium chromate, and so more would dissolve in this situation. All right, that's the end of these. I'll see you in class.